please read the section on 595 to 596 that prefaces example 3 with carbon dating. It'll explain what carbon dating is and how they came up with the formula. So the formula we're going to be using is above it, above example 3. Carbon-14 has a half-life, so half of carbon-14 decays after 5,730 years. From this assumption, find the approximate age of a skull found by an archaeologist if the skull has 67% of its original carbon-14 concentration. Okay, so we start with the half-life. So I know 67% times A. A is the original amount of carbon. So we don't know the original amount. We just know that 67% of it is still there. So then we have the original amount of carbon. Half-life means that every amount of half-life it takes, which is 5,730 years, half of it is decaying, so that's my rate. And my exponent is the number of years it is, but it has to be a fraction of how long it takes for half of it to disappear, which is 5,730 for carbon-14. And we want to find out how long it takes to get to the 67%. Right now I have two variables. I have A's and T, but if I divided both sides by A's, what happened to these? They turn into 1, so they actually just go away. Now I have a base of 1/2, exponent of T over 50730 equals 67%. I could write this as log base 1/2, or I can take the log of both sides. In the book, they take just log. You could take the natural log if you wanted. It doesn't matter as long as the log you take has the same base on both sides. All right, so this whole expression up here is my exponent, so I'm going to keep the log of 67. I'm going to move my exponent as my coefficient, and this will now still be log of 1/2. I'm going to divide by log of 1/2, so I get log of 67% over log of, if you want to make it a decimal, just so you keep all decimals together, you can, equals T over 50730. To undo that division, I'm going to multiply by 50730 on both sides, and T is going to be that. So I'm going to take a log of 0.67, enter, divide by log of 0.5, enter, times 5,730. I'm doing it step by step just so I don't have to deal with parentheses, but you can, I'll make it approximate, 605, we'll go there. And this is in years. So the carbon dating of this skull is approximately 3,310 years old. Cool. All right. And they do want you to check, so more than half the carbon of 14 was left, the age should be less than half-life. Because 67% is left, I would expect 50% to be left at exactly 5,730 years. This should be less than 5,730 years because I have more than half of the carbon. All right, change of base theorem. If I have a log of some base of some argument A, I can rewrite this as log of A over log of B. The book adds the subscript base for C. As long as the base is the same, it doesn't matter. So this could be log base 10. It could be natural log. As long as the base is the same in the numerator and denominator, and your A goes to your numerator, B goes to your denominator, then these are equal. So I go back to page 1 with my example from here. Notice how when I took the log base 3 of both sides, I ended up with x being equal to log base 3 of 27. When I did it another way with just base 10, I got x is log base 10 of 27 divided by log base 10 of 3. So it is the same thing no matter which way you write it. One of them is more convenient than the other. Typically this is more convenient and it's quicker for your calculator to figure out using base 10 or natural log because those are quicker buttons to access. And we didn't used to have the change base thing built into our calculators. So does it really work? Plug in some values, see if it actually works. And from what I just said, why is it useful and revolutionary?